we did officially start at 6:25. So, welcome this morning, everybody who's here. Yeah, thank you. They're applauding for me if you can't hear that. Standing O right there. Okay, so we're going to talk about solids now. And this is actually a little bit easier, and this one will be actually a little bit shorter than the video from last night. The weird thing about the videos is you're going to be getting this material about one day before we talk about it in class, right? So we're talking about solids here in class today. We're going to talk about phase changes and all that stuff. So you just have to kind of shift your brain back and forth a little bit, but that's the only way I could think to do it. So, so anyway, when we're talking about solids, I mean, we all know what a solid is. It's not a very difficult concept, right? It's closely packed molecules. They're connected with intermolecular forces, okay? And that's basically all there is to it. Not really, but that's the simple definition of a solid, okay? Solids kind of fall into two groups. Now, there's not a lot of blanks to fill in on these notes, so you're just going to have to kind of pay attention as we go through. There's a few examples here, okay? But make sure that you're writing your questions if you have them, and I'll see if I can answer them. Two groups that we can separate solids into. One is called crystalline, okay? And in a crystalline solid, there's a very ordered arrangement, okay? And so with these ordered arrangements, I mean, you can look at this and you can tell, okay, this is very, very structured, okay? If I take one piece of this solid, it looks the same as every other piece of this solid, right? So this unit right here looks exactly like this unit up here, or this unit over here. It doesn't matter where I look, okay, the solid looks the same all throughout, okay? So that's a crystalline solid. Now, an example of that is SiO2, which, do you guys know what SiO2 is commonly called? Probably not. I wouldn't expect you to. Well, okay, silicon dioxide is its chemical name. Commonly, that is called quartz, okay? So that's an example of a crystalline solid. Oh, does it say it on your notes? Oh, yeah, it does. There it is. Okay, SiO2, which is quartz. Okay. Then we have amorphous solids. Okay, that's the second group. So we've got crystalline and amorphous, and you kind of need to remember those two terms, all right? Those are the two big ones. There's not any particular order. So you pick one part of the solid here, right? This little section looks a lot different than this section. So you can't just pick any one particular place and expect it to look all the same throughout, okay? So an amorphous solid, an example of that is SiO2. Kind of strange, right? Okay, quartz glass. So glass is actually known as an amorphous solid. So there are different ways that silicon and oxygen can arrange themselves around one another, or these SiO2 molecules can arrange themselves around one another to either be highly structured or to be a little bit more disordered. What do you think might cause something to become a little bit more structured, possibly? Okay, so maybe we put something under a lot of pressure over a long period of time, and we sort of order those molecules a little bit more, right? Can you think of another example of something that's kind of like that? You put it under a lot of pressure, maybe a lot of heat, and it becomes very ordered, very hard. Maybe like the hardest substance on the Earth in existence. Play-Doh? Okay, Play-Doh is very hard, yes. I was thinking of something more like geological, something that, is fairly valuable. There we go, diamonds, right? Okay. Play-Doh might be an example of that. I don't know what happened. I think maybe just the moisture is evaporating out of the Play-Doh, possibly. I don't know. I'd have to look that one up. Okay, so that's the idea, crystalline versus amorphous. You guys need to know the difference between those, all right? As you say, attractions in ionic crystals. Okay, so now we need to talk about ionic crystals a little bit and how they form. This is as close as we're going to get this year to geology, okay? I don't know when the last time was you guys took geology. It's probably been maybe 8th grade, 7th grade, something, when you talked about rocks. Okay, it's been a while, I'm sure. But this is the closest we're going to get to this, okay? The way that rocks are structured has to do with this arrangement of the ionic crystals, okay? And what happens here is these things, you can kind of think of them like ping pong balls, right? If you're going to arrange a bunch of ping pong balls on top of each other, they're going to layer themselves so that they pack in as tightly as possible, okay? And so there's some different arrangements you can have here. This is a close packed layer right here, okay? And you've got 1, 2, 3, 4, 5, 6, 7. No, I just counted one of those twice. What is this? 1, 2, 3, 4, 5, 6, 7. Okay, so there's 7 here in this layer. And then if you flip that horizontally like this, you can pack these on top of one another. But see how they're kind of staggered so that you can fit them in as closely as possible, right? Okay, so that's how that's working. So what these create are these things called unit cells, all right? And there are some different arrangements that these ionic crystals can have based on their size, based on their charge, that sort of thing. Okay. So when we say a unit cell, again, we're talking a lot more about the crystalline solids right now, because the amorphous, I mean, you can't really talk about how they arrange themselves because it's always going to be different, right? But with the crystalline solids, there's always a very definite arrangement of these ionic atoms for one another. Okay, and it's just this repeating pattern that builds these big blocks. And so one type of structure you can have is a primitive cubic, and as you can see there, you have atoms at each corner of the cube. Okay, so that's one way it can be arranged. You can also have a body-centered, where you have atoms at each corner, and then you've got one in the center. And you can have a face-centered, okay, where you've got one atom on each face of the cube, and then atoms in the corners as well. All right, that obviously is a lot more closely packed than either of these two types. So in a primitive cubic, if you think about it, really this is about 1/8 of an atom right here at the corners. That's inside the cell itself. Okay, what we're talking about here is we're looking at a particular cell, and we're saying, okay, how many atoms are actually in that one cell? Okay, so if you come back over here, just notice, I mean, it just looks like the very tip of this thing right here is actually inside the cube. The rest of it is outside the cube. You guys see that? Okay, and so we say that about 1/8 of each of these atoms is inside that particular cube right here. Okay, and so if you have 1/8 of an atom at 8 corners, then that means that we have a total of 1 atom inside that cube, right? We've got 1, 2, 3, 4, 5, 6, 7, and then you can't see the back one over here is 8. Okay, and so if each of those is 1/8 of an atom, and there are 8 of them inside the cube, then that's a total of 1 atom inside the cube if we're adding up all the different parts. Okay, with a body-centered cubic, we've got 1/8 of an atom at every corner, and then we've got 1 entire atom in the center of this thing. Okay, and that atom is completely inside the cube. So we end up with a total of 2 atoms inside that cube with that arrangement. Okay, and then here, if we've got a face-centered, I just forgot. Does the face-centered have? No, the face-centered does not have one in the center. Okay, so we've got each of these on the face of the cube is 1/2 of an atom. Okay, and so we've got 6 of those, so that gives us a total of 3 atoms, and then we've got our 1 atom from the 8 corners, so that's going to be a total of 4 atoms there. Okay. Now, the reason that we even talk about this is because if you look at the way these things are structured, you can actually tell what the ionic formula for the compound would be. Okay, and we talked about this a little bit last year. Is this anything different than what I already said? Determining how many atoms of each... Yeah, I mean, that's essentially what I just said. So when we look at how many atoms of each element are inside any given cube, we can tell what the ratio of those two are to one another, and we can figure out the formula. It's usually easier to cross charges than think about unit cells, but this is another way to figure out the formula for an ionic compound. Okay? So on your sheet, obviously there's no color, so instead of saying gray or green, I said large or small. Okay, so on that first one, letter A there, the large atoms are the chlorine atoms, and the smaller ones are the cesium atoms. Okay, and so really we only have one smaller atom there, the one in the very center. Okay, and so if you think about this, there's one cesium inside the cube, right? So we can count the number of each of these that we have. So there's one cesium here in this cube, and then how many chlorines do we have inside this cube? And when I say inside the cube, I mean inside the cube, okay? Just one, right? Because there's an 8 at each of these corners, okay? And there's 8 of them, so there's one of each of these inside the cube. Does that make sense? So what that shows us is, that shows us the formula for cesium and chlorine should be just CsCl, okay, cesium chloride. Does that kind of make sense? I mean, again, that's not typically the way that you're going to be asked to figure out the formula of an ionic compound. It's much easier to look at the periodic table and say cesium has a 1 plus, chlorine has a 1 minus, so 1-to-1 ratio there, right? But this is another way to look at it. All right, and then the usefulness of this is it really does show us geometrically this is how these things are arranged in space, okay? And then you've got something like B here. Now this is a little bit tough to tell exactly what's happening on this one, whether these things are on the face or whether they're on the inside. What it looks like to me is that these gray ones here, the zinc, are actually on the inside of the cube, okay? And then you've got the sulfurs that are kind of, it looks like a face-centered cubic around the outside of the cube, okay? So how many zinc atoms do we have here? If all of them are inside the cube? It's 4, right? You guys see the 4 gray atoms there? And then let's figure out how many sulfurs we have. So this is face-centered cubic, so each of these right here on the face represent half of an atom because half of it is inside the cube. So 1, 2, 3, 4, 5, 6, so that's 3 of those, okay? And then we've also got them at all 8 of the corners, which gives us an additional 1, okay? So we're also talking about a total of 4 for the sulfur, okay? So again, the formula here would be ZnS. Now, does that fit with what we know about the charges on those two elements? You guys remember what the charge on zinc is? It's always a 2 plus, right? Okay, and then sulfur is a 2 minus. You can tell by looking at the periodic table. So that works. And then the last one here, again, let's assume the blue dots are inside the cube. It is really hard to see these pictures because it's hard to see 3 dimensions in a 2-dimensional drawing. But the blue ones are the fluorines. And so we're going to say that there are 8 of those. You guys see all 8 of the fluorines here? And then how many of the calciums do we have? Okay, yeah, this is the same packing as with the sulfur over here, right? So we've got 6 at the face, so that's a total of 3, and then 8 at the corners, so that's going to give us another 1. So we've got 4 of those. So what would the formula be for that? Right, it wouldn't be Ca4F8, right? You want to reduce that, so it'd be CaF2. And again, does that fit with what we know about the charges on those particular atoms? Yeah, okay. So that's another way of looking at it. Again, that just shows how these things are kind of arranged in 3-dimensional space. We've talked more about that with covalent compounds, really, than we have about ionic compounds, so I want to just mention this. Because there's really no... You don't have to talk about VSEPR or VSEPR, I guess, the valence shell electron pair repulsion or anything like that for these, because they just kind of arrange themselves, they pack themselves in as closely as they can, okay? All right, so here are the types of bonding that you can have in a solid. You can have molecular bonding, right? And again, I want to make a distinction here. We're talking intermolecular forces when we're talking about these, okay? You guys understand what I mean when I say that? The difference between intermolecular and intramolecular forces? Because I think this is something that confuses students sometimes. And I talked about this on the video last night as well. But let's say that we've got something like, well, let's say we've got a carbon atom, right? So, I mean, when we're talking about molecular attractions here, okay, what we're talking about is the attraction of one carbon for another carbon. Now, why would one carbon be attracted to another carbon? It doesn't seem like that would be the case. What would be maybe a reason for one carbon being attracted to another? Because they have exactly the same electronegativity, right? Why is one xenon atom attracted to another? Why is an F2 molecule attracted to another F2 molecule at all? You guys don't remember this? Okay. You remember talking about induced dipoles? Okay, that's where London dispersion forces come from, right? At any given moment, all of the electrons on one of these carbons might be on one side of the atom, okay, which induces a dipole in another carbon that's next to it, and so you have these loose bonds, okay? Now, these attractions are weak, right? So molecular solids, what kind of boiling points do you think they're typically going to have, or melting points, I guess I should say? Is it easy to melt a molecular solid, or is it something you have to really heat it up to a very high temperature? Now remember, to melt a molecular solid, all you have to do is break the bond right here between the carbons, right? Is that a hard thing to do? Not with an induced dipole, right? Okay, not with London dispersion forces. Those are reasonably weak in most things, okay? Especially in smaller molecules like carbon. So this is going to have a fairly low melting point. Now, carbon's a little bit weird. Carbon likes to burn before it melts, so that's probably a bad example, okay? But most of these molecular solids, they have very low melting points. Now, that's, it sort of depends on the arrangement. This says low to moderately high because there's a lot of things that can happen there. If you have a really big molecule, then London dispersion forces actually are strong, and then it's going to have a fairly high melting point, okay? So here's some examples of some of those types of things. Now again, with molecular solids, we're also talking about, a molecular solid would also be ice, okay? So ice has a lot stronger intermolecular forces than something with just London dispersion forces, right? Okay. So when we get to covalent network, okay, that's another type of covalent solid that you can have, or molecular solid. Examples of this: diamond, quartz, those sorts of things, okay? And these are connected in a network of covalent bonds, okay? And it's a very structured network. The more structured it is, the more repeating the patterns are, the harder, the higher the melting point, that sort of thing, okay? So these are kind of like special cases. And honestly, the two that you really need to know for the AP exam, you need to know diamond and you need to know SiO2. I mean, those are the two examples they give you right there. You need to know both of those, okay? Because they will give you, you have two questions on your AP packet, I think, this time around, that ask you specifically about, they give you SiO2 in a list of things, and they ask which one has the highest melting point, and you have to actually figure that out, okay? So, that's the covalent network. Ionic solids, okay? How high are the melting points on ionic solids? Fairly high, right? Do you guys remember the lab we did last year where you had ionic versus covalent? Okay, and you tried to melt them. The ones that melted were typically the molecular solids. The ones that didn't melt were typically the ionic solids. Okay, and then you've got metallic bonding also, and we'll talk about that a little bit in just a minute. But the metals, if you remember this from last year, those are the hippies, right? That's the hippie commune, the sharing of the electrons, that sort of thing. Okay, so here's an example of this is actually two examples of covalent network solids. One is graphite, one is diamond. Okay, so I can't highlight both of these at the same time, I guess. Here's what's going on with this. This is diamond right here. Okay. And you guys see how actually all of these are covalently bonded to one another, okay? You see that? So that's like diamond, okay? So to break one of these, you have to break, we're not talking like London dispersion forces or anything like this here. This is a bunch of carbon atoms that are actually covalently bonded to one another. They're actually sharing electrons between them, okay? If you get a bunch of carbons doing that, you put it under enough pressure and enough temperature for a long enough period of time, you can get the carbons to actually share their electrons that way, okay? That is a very stable arrangement, and that's why diamond is the hardest natural material. I think that's still the case. It's the hardest natural material that you can find on Earth, okay? It's the top of the hardness scale for sure. But then you got something like graphite, which is in your pencils right now. Okay, how easy is it to break graphite? You wouldn't be able to write with it if it wasn't easy to break, right? It's very, very easy to break it, okay? So obviously there's something different going on there. What happens with graphite is you get these layers, okay? So you've got a layer here, you got a layer here, all right? This layer is covalently bonded. Everything in this layer is covalently bonded to everything else in this layer. But between the layers, these are just London dispersion forces right here, okay? So the only thing that's holding these two layers together is this fairly weak intermolecular attraction. So that's why it's so easy to break your pencil with this arrangement, and break the lead on your pencil, okay? And that's why diamond, made out of exactly the same material, because both of these are just carbon, right? That's all your pencil lead is just carbon, okay? But this one has been put under so much pressure for such a long time, these things have actually come to share their electrons between each other. And here, you've got sharing of electrons in each layer, but the layers are very easy to break off from one another, okay? Does that make sense? It's also like graphite, it sort of feels slippery when you do this. You're sliding the layers past one another is what you're actually doing. Okay, and then a metallic solid. This is the last one here. They're not covalently bonded, these atoms, but there is a high amount of attraction between the electrons, especially the valence electrons, in these metal atoms and the nucleus of each of the metal atoms. Okay, and so again, this is sort of the hippie commune thing, right, where they're sharing their electrons. These electrons don't necessarily belong to any one individual nucleus here, okay? But there are enough of these electrons floating around that they keep the nucleus of these metal atoms together, okay? And obviously these are fairly strong forces, right? Now, how do we know that? What are metals typically at room temperature? They're typically solids, right? Okay, and you usually have to get a metal fairly hot to melt it, okay? That's not always the case. There are certain metals on the left side that are fairly soft and not that difficult to melt, but actually the things on the left side will tend to react before they melt also because they're just trying to get rid of their one valence electron. But the valence electrons are delocalized, right? They're just kind of floating free. And that's the reason that metals are such good conductors of electricity, even as solids, because they have these free-flowing valence electrons. And in order to conduct electricity, you need the electrons to be able to move throughout the solid. Okay? Let's see, what else? Oh. So, thanks for coming so early this morning. This was a short one. They're not all going to be this short. But are there any questions on this? Because we do have a little bit of time here. And since I'm done, you can just yell them out if you have questions. Oh, okay, good question. Here's what I would know from that chart. Again, I would know the covalent network solids, okay, especially diamond and SiO2. Those are the ones that I see come up over and over and over again on the AP exam. I would know the 4 different types of crystalline solids that you can form, okay? I don't know that you have to have this whole chart memorized. Honestly, you probably know a lot of this anyway, because if you think back to the covalent ionic lab that we did, okay? The covalent ionic lab we did is essentially comparing this group and this group, okay? So if you can kind of remember that lab, then you should be able to remember, oh yeah, the ionics were the ones that didn't melt, okay? And most of the covalent compounds did melt. Okay, so typically these have lower melting points. What else from this chart would be really good to remember? Honestly, it would be good to know this chart, okay? Not that they're ever going to make you reproduce it, or I'm not going to make you reproduce it, but just knowing everything that's on here can only help you with those kinds of questions that they would throw at you on the AP exam. Yes, ma'am. Okay. That's a good distinction. So hydrogen bonding versus covalent bonding. Is that what you're talking about? Okay. So hydrogen bonding is a strong intermolecular force. It's the strongest of the intermolecular forces, unless you count ion dipole. I guess that would probably be a little bit stronger. So the strength of the intermolecular forces kind of goes like this. You got London dispersion is typically the weakest, given, again, this is very dependent on size, okay? But London dispersion, and then you've got dipole, and then you've got hydrogen bonding, and then you've got ion dipole. Okay? Those are all the intermolecular forces, the forces between the molecules. Okay? So one of the highest intermolecular forces is hydrogen bonding. And I have another place where I could draw this better. Here, I'll just do it over here. This has nothing to do with this slide, but so you've got two water molecules, okay? Looks something like that, okay? The hydrogen bonding, we're talking about this attraction right here, the attraction of that hydrogen for that oxygen, okay? This is between two different water molecules, all right? So this is a very strong bond, but this bond right here is not nearly as strong as the covalent bond inside the water molecule itself, okay? Does that make sense, the distinction between those two? So you have to think about the intramolecular forces, the ionic, the covalent bonding, versus the intermolecular forces, the hydrogen bonding, the London dispersion, dipole, okay? Because those intermolecular forces are just between molecules. The forces actually within a molecule are much stronger, okay? All right, any other questions? Those are good questions. All right, we are done for the day, so I guess enjoy your next 20 minutes. Wait, that wasn't right. End show, there we go. It's going to take 10 minutes for me to figure out how to end the video.